So my name is Jose Martin Garcia. I'm one of the Geo developers at Wolfram. Today, I'm going to report on progress in Geo Computation. So the talk will have basically two parts. In the first part, I'm going to talk about geographics updates, and I will talk about 5 specific things that we have improved or updated in the code of geographics. And then in the second part of the talk, I'm going to introduce a new area which plays the role of connection between the Geo project and the Astro project. And it's based on this new function called Geo Orientation Data. So let's go first for the geographics updates. So Francisco explained in his talk yesterday that we have changed the background in geographics. This is a step towards the goal of having fully vector maps in geographics. And so what we are doing this time is to have a image tiles in the background plus vector maps. So here, for example, in this case, we have the tiles, and you see that the labels are vector primitives. So an advantage of this way of proceeding is that in the same way that we have here the labels with Mercator projection, now we can use the same labels with other projections, for example, with transverse Mercator. And in this case, the map is very similar, but you see how in the Mercator projection, northern areas get too big. Here we see how the parallels and meridians are converging towards the north, and the transverse Mercator projection gives you better results for areas that are vertically elongated. In this case, it's more or less the same. Just in case you want to go back to the previous behavior, we have this variable that you can set to legacy, and then here you will get the same map that we always got until now. The same variable can be used to reproduce the vector results. And so if you just want to have the result that we will eventually have fully vector, then just do that and you will get fully vector maps. And just by unsetting the variable, we get back to the what we call the hybrid GeoBackground type. Okay, so in order to do that, something that we did is to have lists of GeoBackground, which was also shown by Francisco yesterday. And so in this case, we are having effectively what we now have as default, which is the combination of our traditional tiles with no labels plus vector labels. And an advantage of this is that now you can control independently the parameters of each geostyling. For example, here, something that many users had complained, some users had complained in the past, is that we had sometimes too small labels, but because now they are independent from the background, we can control the zooms independently. So in this case, just to make it more apparent, this map, which is zoom 7, I'm going to decrease the level of the images, and I'm going to increase the level of the labels, and you'll see how we get more labels here. And right. In some cases, opacity may be needed too. So for example, if you want to overlay, say, the roads and the relief map, just because you want to stress the fact that there are lots of mountains in this area, then because these are both opaque layers, you need to add opacity to the one that you put on top. So we have the GeoBackgrounds, of course, are read sequentially. So we first lay out this one, then this one, finally the vectors. And so we get this map. Okay. Another thing that we have changed in version 13 is the default Geo Range. What does that mean? So in the past, geographics bracket always show it a local map. However, now it shows a world map, for example, this case. So this is the case for other projections too. And notice how the map is centered at your geolocation. So in that sense, we are kind of acknowledging your location, but in cylindrical projections, it will be just a meridian. In azimuthal projections, it will be really your location will be at the center. So how does this work? So the idea is that if a map doesn't have any geolocation information whatsoever, then it will choose the geo range of the world. However, if we still have some location information, for example, my geoposition, we will still do what we used to do, which is reporting a local map, right? Because you are asking explicitly for a given geolocation. If you provide something that has polygon information, like for example, this entity, then it will show the region corresponding to the polygon of that entity. And why do we do this? So the thing is that whenever you had an invalid map, geographics would ignore, whenever you had invalid input, geographics would ignore that input and would fall back to the default map with no information. So it was very frequent to get very local maps. So the idea is that now when there are errors, somehow we go back to a more global map. Another thing we have changed in this version is that geographics is now more lenient with errors. And so, for example, in this particular case, in which there was an invalid primitive, it used to return a blank map, which wasn't very useful. So now geographics, it's able to remove, it will still report a message saying something went wrong, but it will remove and without pinking invalid primitives. For example, in this case, we have a red parallel here, a blue invalid geopath, and a green meridian here. So we get these two. And we do this. Okay. Another thing we have improved in recent versions is the handling of geo labels. Yes. So in this map, so this is more what I want to show is clearer in a region with mountains and close to the coast, like Monaco. So the idea is that until now we were having always straight labels, and in version 12.3 we added the ability of having the labels follow the lines. So we do this for curved streets, for rivers, and other line elements. And so this, of course, represents a slightly more complicated collision problem in which we have to break the individual texts into their letters and perform the collision algorithms already at the level of the individual letters, computing their boxes, etc., etc. So it's a bit slower, but the results are much better. And as Francisco showed yesterday, we have a collection of internal variables and method options in order to switch between these various possibilities. So if for some reason you want to go back to the previous straight labels or something like that, do contact us and we'll let you know how to do that. And another thing that we have improved with respect to labels, which I think Francisco also showed yesterday, is the fact that now when you rescale the maps, they rescale with the map, right? So you can have the same map at all scales looking consistently with respect to labels. Another thing we have added is support for Epilogue. So it works this way. So in geographics, we can have, as usual, our first argument with the geo input, the geo primitives. Now we can add Epilogue. So the thing is that when we add Epilogue, Epilogue represents something that we have added and as an afterthought, and it doesn't change the estimation of geo range or geo projection, right? And so you see here how this blue polygon with Germany doesn't change the estimation of the Geo Range and projection, which is controlled by the polygon of France. Compare, for example, with this other map in which we put both things together in the first argument, right? And you see how both now are taken into account for the estimation of ranges and projection. And another thing motivated by the addition of flight data is that we have extended this primitive geovisible region and its boundary counterpart to take multi-position specs. So we were always able to take one object with height elevation and show the region of the world that is visible from that point, or vice versa, the region of the world which can see that object, that point. So now what we can do is that we can take a collection of points with elevation, for example, of the type that is returned by flight path in flight data. So these are points with heights, right, ranging from 13 meters to this number of meters. And now we can do this. We can show, you see, it's the same geoprimitive, but now with all the locations. Now we can show all the visible range boundaries, all these almost circular regions. And you see how interesting it is that we see how the circles are growing. This is when the plane is going up, right? Then and there is some sort of caustic here, and then it starts moving and ends up here, going down again. So we can see the region of the wall that you would be able to see from that plane as it flies from one place to another. You can do the same thing with georegion, with geovisible region itself. And so just by using low opacity, you get the region that would be visible. Okay. So yeah, that was first half of the talk. And yes, that finishes the review of updates of geographics for this version. So now I'm going to talk about the second part, which is a new function which sits in between the Geo project and the Astro project, which we will discuss more in a talk in less than an hour, in another talk. So the problem is the following. So what is the orientation of the Earth in space? So rather than looking at the Earth only, maps on the Earth, now we are interested on the problem of the orientation of Earth in space. So the goal here is to transition from the very precise positioning that geoposition allows to something similar in the Astro project, an object that in the future will be called Astro position. So in order to do that, and because we are interested in looking at the universe from the Earth, from the locations on the Earth, we need to have very good control on the relation between the frames on the Earth and the frames that are used typically in astronomy, like celestial frames. So this is a diagram that shows more or less what the problem is. So if we take, there are multiple frames in astronomy, and I'm not going to discuss that here, but let us suppose that we take the frame associated with the ecliptic, right, which is this blue structure. So this would be the z-axis, and this would be the xy plane. And then we have a frame on the Earth, which would have also its z-axis, more or less the rotation axis of the Earth, and its equator, right? And so these are going to be moving with respect to one another. We know that there is the 26,000 years precision movement of the axis of the Earth. And then, of course, there is a much quicker, much faster motion of the Earth around itself, around this axis. So this is a problem of related frames. So on the Earth, we have the frames, and we call them datums, and we have a number of them. Actually, in version 13, we have increased this list. We have added a few recent of the ITRF frames particular, this is the last one. And I think they are working on another one called ITRF21. This is not out there yet. And we have also added the corresponding sequence of European frames, which are slightly different. So you can transform between them, and you see how the European frames have evolved too. And another thing is that in this area, there is usually the distinction between the systems. This is the International Terrestrial Reference System, which is the idealized versions, and its realizations. So this is like the definition that they want to achieve. And this is how the different frames via a specification of the coordinates of locations are given in each of these realizations. And so we will be referring here to the systems themselves. So as I said, there are multiple celestial frames, but in recent years, there is one which is being used the most, because it's a reference system that is fixed, as much as we can tell with our current technology. It's fixed with respect to distant quasars. And so the main thing here is to relate coordinates or vectors given in this frame to vectors given in this other frame. There's an institution, the International Earth Reference System Service, I think it's called. It's very interesting web, I recommend, and in which they give continuously, they report the orientation of one with respect to the other. So what we are doing with this function, the orientation data, is provide data obtained by from the IERS. And before continuing and showing examples, I want to give you an idea of the precision level that we want to achieve. In geocomputations on Earth, the computations are precise to much less than a millimeter, around micrometers, I would say. And for the current precisions of GPS, which is of the order of a centimeter, this is enough. And these are computations on the ellipsoid, right? Not on the topography. For that, you need, of course, the topography information, which is usually less precise. So in astro computations, we want to be precise to angular distances of around a milliarc second. And to give you an idea of what that means, let us compute, for example, what would be a milliarc seconds on the surface of the moon as seen from the Earth. It would be around 2 meters. That's a very small angle. Or for example, if we look at a distance on the surface of the Earth from the center of the Earth, it would be about an inch, about 3 centimeters. So that gives you an idea of the small angles that we want to achieve. I mean, a small angular precision that we want to achieve. In terms of time, how much precision is a milliarc second? Well, it's about 10 minutes. So you see that in order to control angles of milliarc seconds, we need to have very good precision control on precision. And if we look at the faster motion of Earth rotation, it's even more. We need of the order of less than a millisecond in time in order to control rotations of order 1 millisecond of arc. So how is this problem treated? So what is usually done is that the relation between the frame fixed on Earth and the frame fixed in the celestial sphere is broken into 3 rotations. The first one is the rotation that follows the rotation axis of the Earth in space. And so this is, remember, the precision motion. That angle is the obliquity angle, which changes. So that's the current value of the obliquity angle. And for example, if we compute dates from 10,000 years ago to 30,000 years in the future, so we get something like this diagram. And you see how the angle, this is 24 degrees, this is 23 degrees. So the angle is changing, and we are about here, more or less, right? This is very important information for climate change and things like that, because depending on the obliquity of this angle, the Earth will get more or less light in different areas. And what about precession itself? So let's compute rotation matrices. So the to get an idea of the angles involved, I've constructed this function here, which takes the eigenvalues of a rotation matrix. Then it takes the logarithm to get the exponential. This is the imaginary part. And then, because this is going to produce two complex conjugate numbers and a 1, we just get the imaginary part of the largest one, which is in radians. We convert it to degrees, and then we multiply by 3,600 to convert into arc seconds. So this rotation of the frame associated to the Earth around the celestial reference frames is also broken into 3 parts. There is a part which is usually called bias, which is just an original value. It's fixed. When they started measuring precession, this was the matrix to start with, which is very small. And it's about 23 milliarc seconds. But because we want to be precise to milliarc seconds, we want to take that into account. Then we have the precession matrix, which is changing. I mean, every time I reevaluate this, it will change a little bit because it's changing with time. And this is in the thousands of arc seconds. So this is a large value. As I said, it goes round once every 26,000 years, more or less. And then there is a small oscillation called nutation, and we can get also the nutation matrix, which it's in the order of 10, 20 arc seconds. So the product of all 3 of them is the matrix we are interested in, and this matrix is the one controlling very precisely precession for the Earth. Okay, so now we know where is the axis of rotation of the Earth with respect to space. Now we want to know how the Earth rotates around that axis. So we consult again geo orientation data. And in this problem, the thing that we are most interested in is the duration of the day, because it happens that the duration of the day is not constant. It changes around this value, which if we show all digits, we see that it's not exactly 86,400. And if you want to know this value with errors, then there is the so-called day duration excess, which shows the result, the variation with respect to this value in milliseconds. So you see this, there is a precision of around microseconds. This is something that changes due to tidal break-in, and it's getting usually, the day is getting longer and longer. However, if we look at the data in the last few years, interestingly, it is getting faster recently. The trend is to get slower, as I said. So we have data, very precise data measured daily from the 60s. And before that, we have just data corresponding to several models that have been adjusted to astronomical results. And yeah, let's see if this finishes, right? And for dates before that, we have models which are even more coarse. But you see how 1,000 years ago, a day was about 10 milliseconds shorter. Of course, 10 milliseconds is very little, but over 500,000 days or something like that, this is many hours that have accumulated. That this is important to look at results from eclipses thousands of years ago. So all this information and many more things related to this is stored in geo orientation data. And finally, something interesting is that the axis of rotation of the Earth does not correspond exactly with the geographic axis of the Earth. if we were able to show where the axis of rotation is, the instantaneous axis of rotation is on the Earth, we would see it moving with respect to the ground, assuming some average ground, ignoring tectonic plates. So this is called polar motion. It's the motion of the polar axis on the surface of the Earth. And it's something of the order also of fraction of seconds. But again, because we want to be precise to milliards seconds, we have to take this into account. So how has this been evolving? We compute, say, all days in these 5 years, and we compute the values of polar motion for all these dates, which are close to 2000. So if we plot this, we got a result like this. And this is the geographic North Pole. This is the orientation. So this is direction is this one, and this direction is this one. And you see how this is moving around circle per year, more or less, right, in this area here. And to get an idea of size, we do this to convert to meters, and we see that it's in the order of 10, 15 meters, right? This is very small, but it is moving. And this is something that needs to be monitored by the IERS. And just to give you another sense of what this is doing, these are years, right? So we see how the Earth rotation axis is moving on the ground as the years pass. So it's going in this direction. So now I've oriented Greenwich in this direction for clarity. Okay, I'm running out of time. And so my conclusions are those. We have shown several improvements and updates in geographics in our progress towards full vector maps, and we have introduced a new function, geoorientation data, which establishes a connection between the Geo and Astro projects. Okay, now let's see if there are some questions. Do you know what ephemerides are being used? Is the yes. So this, we are using at the moment some approximate ephemerides, but we are going to improve these. I will explain this in the Astro talk by connecting to the NASA SPICE kernels for better ephemerides. Yes. Can lines and curves drawn on a sphere be projected on a flat image using the geoprojection feature of geographics? Well, we can project lines and curves that are specified via the geographics language, not via the 3D spherical, say, primitives, and then project. So let me look at chat. I've noticed that the internal representation of vector maps has lots of rich metadata annotations. Yes, we will provide access to those primitives and ways to restyle them in the future, but we first need to get the default values properly processed and fast. In which version will Epilogue work in geographics? In version 13. Yes, in the new upcoming version. And Mapbox, yes. So our vector tiles use the same format of Mapbox. So whatever you can get in that format eventually will be able to be read. So we are preparing for that. 3D map. Yes, there is 3D map information there. Yep. Okay, so I think that completes my time. Thank you very much. And if you have more questions, please contact us during the conference or by email. Thank you very much.